Have you ever been there? That moment you log into your university's registration portal, right? Clutching this perfect schedule you planned out,
Oh, yeah.
only to find like three of your core classes overlap and that one elective you really wanted is just full.
Happens all the time.
It feels like the university is almost actively trying to thwart your plans, doesn't it?
What?
Well, it's not just you. This task of course scheduling, it's actually a surprisingly complex puzzle for millions of students, like every single semester.
It truly is a universal challenge.
Hmm.
What we call the university course timetabling problem, or UCTP.
Mm.
It's known for how many tricky rules and just moving parts it has.
Right.
Trying to do it all by hand. It's a massive job, really prone to errors, and frankly, just inefficient.
Well, today we're taking a deep dive into a really interesting research paper from Thammasat University. It's titled Planning a Timetable for Deciding to Registration in Course. And our mission, really, is to unpack how a mathematical approach, specifically something called integer programming, can maybe cut through this complexity and actually help you complete your academic program in the shortest possible time.
Sort of like a roadmap.
Yeah, exactly. Think of it as a shortcut, maybe, to navigating that whole academic maze. Okay, let's really dig into the pain point here first.
Hmm.
Why is building a university timetable such a headache for students? I mean, you said doing it by hand sounds almost impossible.
Yeah, well, the problem goes way beyond just, avoiding classes at the same time.
Right.
It's about navigating this really intricate web of academic program requirements. You've got a ton of prerequisites.
Courses you have to take first.
Exactly. And co-requisites, things you have to take together. Plus courses that might only pop up in specific semesters.
Ah, okay.
So any little deviation from the standard plan, like say you withdraw from a course, or maybe you don't pass one, that can create this whole cascade of complications. It just pushes your graduation date further and further out.
Yeah, that's where it gets really frustrating, isn't it? Like, imagine you're following your study plan, everything's going fine, then you have to withdraw from just one course, let's call it AM 102. Suddenly you realize you can't register for these crucial follow-on courses, like AM 201 or AM 311, because they needed AM 102.
Right. The prerequisite chain is broken.
Or even worse, maybe that one specific course you absolutely needed is only offered once a year. That can totally derail your plans.
Precisely. And trying to reschedule that manually, it's incredibly time-consuming, and honestly, it opens the door to just making big planning mistakes.
Yeah, I can see that.
And this is really where computational methods like the one in the paper offer such a powerful advantage. They can turn what feels like this overwhelming task into something, well, clearer, an achievable path.
So, okay, with all these complicated moving parts, how do they even start to tackle this with math? What's the secret sauce, that transforms this whole mess into something solvable?
Yeah, the secret sauce.
The paper mentions integer programming. What exactly is that, and what's the main goal here?
Okay, so integer programming. It's a really powerful mathematical optimization technique. Think of it like this. It helps find the absolute best possible solution, like the optimal course schedule, but crucially, only when your decisions have to be whole numbers, integers.
Okay, right. You can't take half a course.
Exactly. You can't take 1.5 courses. So in this research, the main objective is just that. Propose a systematic way for you to register for courses and develop timetables that let you finish your program in the shortest possible time.
So minimum time to graduation.
That's the core idea. It's about finding the fastest, most efficient path through all those degree requirements.
Okay, so it's essentially hunting for that perfect path through your degree. But how does it actually do that? Like, what's the process behind building this optimized timetable? Because, this isn't just about universities, is it? It feels like a great example of how simple scheduling gets super complex with real-world rules.
That's
Whether you're running a hospital or a factory or even just like your family's week.
That's a fantastic point. The complexity scales up fast. So the research breaks the whole process down into 4 clear systematic steps.
Okay.
First, data collection. Second, creating the mathematical model. Third is finding the solution. And finally, result analysis. Should we walk through each one?
Yeah, let's do it. Step 1, data collection.
Right. So first, they gathered all the nitty-gritty details, everything from the applied mathematics curriculum at Thammasat University, specifically their 2018 revised version.
Okay.
This meant every course name, its credit value, and all those crucial relationships, prerequisites, co-requisites, even the specific time slots each course is actually offered.
Wow. Okay. Where did they get all that?
Straight from the source, the university's registrar's website, so official data.
Got it. So that's the raw material. What's step 2? The model.
Exactly. Step 2, mathematical model creation. This is really where the core intelligence lies. They basically translated all those university rules, all the program specifics, into the language of mathematics, into a model.
Okay.
So there are two main parts to this model. First is the objective function. Its job was designed to minimize the total remaining credits you need to graduate.
Ah, makes sense.
It does this by maximizing the number of credits you can successfully register for right now in the current semester, and it takes into account the courses you've already passed. It's all geared towards getting you to graduation as fast as possible.
Okay. Minimize remaining credits.
Yeah.
Got it. What's the other part?
The other part is the constraints. These are basically the rules of the game, all the things the schedule must follow.
Like what?
Well, there's a bench. First, credit load. You have to take between 9 and 22 credits per semester. Can't go over, can't go under. And the whole applied math program needs 133 credits total.
Standard stuff.
Okay. Then prerequisites. You know, the classic. If you want to take AM 451, you must have passed AM 200 first. Or for AM 331, you need AM 201.
Right.
Then there's a really interesting one, previously studied courses.
Oh, what's that?
So for some courses, like SC 173, in their example, you just need to have previously studied SC 123.
Yeah.
Even if you failed it, got an F.
Really? Just taking it before is enough?
Apparently for some courses, yes. Similarly, ST 226 requires AM 102 to have been studied before, and kind of acknowledges that sometimes just the exposure helps, even if you didn't pass the first time.
Huh. That's a neat detail. What else?
Co-requisites, courses you have to take simultaneously. So if you want SC 165, you also need to register for SC 115 in the same semester, or have already passed SC 115.
Okay.
And if you happen to fail one part of a co-req pair, the model's smart enough to make sure you only retake the one you failed, not both.
Good. Saves time and credits.
Definitely. Then the obvious one, time conflicts. Crucially, no two courses the model recommends can overlap in time.
The fundamental problem.
Exactly. They meticulously broke down the entire week, Monday 8 a.m. to Saturday 4:30 p.m., into 36 distinct time slots. Slot 1 is MON 8.00 9.30, slot 2 is MON 9.30 11.0, and so on. Ensures no clashes.
36 slots. Okay. That's detailed.
It has to be. And finally, special course restrictions. These are rules about when you can take certain types of courses.
Like electives.
Sort of. For instance, minor courses. You can only take those after completing 2 years, which is 5 semesters in their system, and you're capped at 5 minor courses total.
Okay.
Project courses are locked until after 4 semesters. Free electives only open up after 6 semesters. And importantly, once you choose a minor group, which you do after 5 semesters, the model makes sure you stick with it. No registering for courses from other minor groups.
Wow. Okay. That's a lot of rules.
It is. That's why doing it manually is such a nightmare.
Right. So that's the model build. What's step 3? Finding the solution.
Exactly. Step 3, solution finding. And this is where the sheer complexity, really hits home. You've got 73 courses in their example, 36 time slots, all those constraints.
Yeah, I can see why that would be an issue. This sounds like it could take, forever to solve, trying every single combination. Isn't there a huge risk of what they call a brute force approach, where the computer just tries every single possibility?
Absolutely. And a brute force approach here would be completely impractical. Forget about it.
Why? Too slow.
Way too slow. For 73 courses, the number of possible combinations is 2 to the power of 73. An astronomically large number. It's practically impossible to compute. Think finding one specific grain of sand on all the beaches in the world maybe times a billion.
Whoa. Okay, so brute force is out. What did they do instead?
They use specialized software, MATLAB's optimization toolbox, and specifically a function in there called intlimprog.
Intlimprog. Okay. How does that help?
Well, this function is incredibly efficient because it uses clever mathematical techniques, things like linear programming relaxation and branch and bound. Think of it like a master detective. It doesn't check every single house. It uses clues to eliminate huge groups of possibilities very quickly.
Smart shortcuts.
Exactly. It zeroes in on the optimal solution much, much faster. For this specific case study, 73 courses, 36 time slots, it found the best timetable in just 6 to 9 seconds.
6 to 9 seconds. That's incredible.
It really is. Shows the power of these algorithms.
Okay, so it finds the solution super fast. What's the last step? Result analysis.
Yep. Step 4.
Yeah.
Result analysis. Basically checking the answer. The output, is a validated timetable. They make sure the number of credits is right, between 9 and 22. They double-check there are no time overlaps. And they verify that all those complex prerequisite and co-requisite rules have been met.
So it delivers a schedule that actually works according to all the rules.
Precisely. A feasible, optimized schedule.
Okay, so this all sounds fantastic in theory, 6 seconds for a perfect schedule. But what does it actually mean for someone, for you, the listener, trying to plan your studies? Does it actually work well in practice?
It does, yeah. The results they reported are quite compelling.
Like what?
Well, for single semester planning, the model successfully generated optimal timetables. For instance, in one test case they ran, it recommended 8 courses totaling 22 credits.
Okay, max credits, but within the limit.
Right, perfectly within the university's limits.
Yeah.
All the recommended courses had non-overlapping times, obviously, and all the prerequisites were satisfied, like if it recommended AM 102, it made sure the student profile showed AM 101 was already passed.
Good. What about planning the whole degree?
For full program planning, this was really interesting. The model was able to map out a path to complete the entire program in just 7 semesters.
7 semesters, that's 3.5 years.
Exactly. A significant speed up potentially. And what was also cool was that the first 5 semesters of the suggested plan were identical for all students. Didn't matter what minor they eventually chose.
Huh. So a common core path initially.
Right. It was only after that point, semester 6 and 7, that the suggested timetables started to diverge based on the student's chosen minor field, which, shows the model is flexible and can adapt to those later choices.
That is impressive, a 3.5-year degree plan. But the research wasn't all glowing, right? It also highlighted some nuances in how effective it was. What stands out to you about the difference in accuracy it had for compulsory versus elective courses?
Yeah, that's a really key insight, and it points to a crucial trade-off, I think. The model showed pretty decent accuracy, 60.18% on average,
Yeah.
when recommending the compulsory courses, the ones you absolutely have to take.
Okay, about 60%. Not bad.
Not bad at all for those. But for elective courses, the accuracy dropped a lot, down to only 31.40%.
Wow, less than a third.
Yeah. The overall average accuracy across all courses ended up being around 45.79%.
So what does that tell us? Why the big difference?
Well, it suggests that while the model is really good, excellent even, at satisfying all those rigid rules and requirement for compulsory stuff,
Right.
it doesn't and currently can't account for things like individual student interests or maybe their aptitudes or just what they want to explore. Those factors heavily influence elective choices, right?
Totally. Electives are where you have some freedom.
Exactly. So while the model gives you a path, perhaps the most efficient path on paper, its perfect path might not always align with the path you actually prefer, especially when you get to choose.
That makes sense. It raises a bigger question for you, the listener, doesn't it?
Yeah.
Where else in your life do you maybe prioritize pure efficiency over personal preference or enjoyment?
Interesting thought. That's a great point. And while it's super efficient for the university and maybe gets you out faster, I wonder if there's a risk of that perfect schedule feeling a bit, I don't know, soulless, too rigid for some students.
That's a valid concern.
But okay, even with those limitations on electives, it still seems like this tool has immense potential, right? Both for students and for the people designing the programs.
Oh, absolutely. The potential is huge. For students like you, it provides an incredibly powerful guideline, especially, like we said, if you've deviated from the standard plan. Somehow maybe you withdrew, maybe you failed a course.
Right, if you're off track. Yeah. It can instantly show you the most efficient way to get back on track and still graduate as quickly as possible. Takes away a lot of that stressful guesswork.
And for the university side, the curriculum planners.
For curriculum planners, it's also really valuable. It helps them design and then validate their programs. They can ensure course sequences are logical, that they're actually feasible for students to complete, and that they provide clear, optimized pathways.
So they could use it to test run a new program structure?
Exactly. Or even identify bottlenecks or weird inefficiencies in programs they already have. Maybe discover that a certain required course combination is causing unnecessary delays for lots of students.
Okay, that's powerful. But this brings up an important question. What doesn't the model capture yet? What are the limitations here, and what's next for this kind of research?
Right, because no model is perfect.
Right.
And that's where the next level of innovation really lies. As we touched on with the electives, currently, the model doesn't factor in your individual aptitudes.
Like, if you're great at math but struggle with writing.
Exactly. Or the perceived difficulty of each course, or even how important you feel a course is for your goals. This means, theoretically, it might suggest a semester where you end up with, say, 3 really difficult, heavy workload courses all at once?
Yeah, that might be efficient on paper, but brutal in reality.
Could be. It might not be ideal for your learning style or even just your well-being that semester. The researchers totally acknowledge this limitation,
Okay.
and they suggest that including these more human elements, things like student preferences, maybe learning styles, course difficulty ratings, that's a crucial area for future development,
Yeah.
making the model not just efficient, but also more human-centric.
Right. Balancing the math with the person.
That's the goal.
So this deep dive really reveals how these mathematical models, like integer programming, can genuinely transform that complex puzzle of university course scheduling, turn it into an optimized, efficient plan, and ultimately help students like you graduate faster, hopefully with less stress. It's just fascinating how pure math can address such, well, such human frustrations.
It really highlights the immense power, doesn't it? Applying these advanced computational methods to very real-world challenges, turning what seems like an overwhelming, messy task into a clear, achievable pathway.
Exactly. And it makes you wonder. Imagine a future where your academic journey isn't just mapped out for speed, but also personalized for your specific learning style, your interests, maybe even adapting on the fly if life throws you a curveball.
That would be something.
How might that change the very nature of higher education for you? Something to think about.